Hello and welcome to Kashmatics. In this tutorial, I'll show you how to use the Trapezium Rule to approximate integrals. I'll show you where the formula comes from and an easier version of it, which is how I like to remember it. Now I'm going to do 3 examples, and for 2 of those, we'll be also calculating the percentage error between the approximation and the actual answer. So grab yourselves a pen and some paper and let's get started. So what is the Trapezium Rule? Now the Trapezium Rule gives an approximation for the area under a graph, and is particularly useful when you have a function which is difficult to integrate or one which just can't be integrated. So let's have a look at this diagram just below. What I've done is I've split the area under this green curve into 4 trapeziums, and the trapeziums themselves, they're counted as the strips, and the blue lines are the ordinates. Okay, so these blue vertical lines are what are called the ordinates. So you have 5 ordinates here, x0 all the way to x4, and corresponding y values, which are the heights of each of these blue strips. So the first thing you need to pay attention to in the question is how many ordinates or strips it's telling you to split the area into. Okay, so remember, if there's 5 ordinates, there's 4 strips. There'll always be one more ordinate than there are strips, but pay careful attention to the information in the question. Now, because these are trapezium shaped, we need to know the area of a trapezium. And the way you do it is you add together the 2 parallel sides, so a plus b, you divide that by 2 and then multiply by the height between them. Now the height needs to be consistent with all the strips. All of these need to have the same width, so bear that in mind as well. So for our graph, this is the area of the first trapezium, this is the second one, this is the third one, and this is the fourth one. So I'll just go over one of them so you understand. So y0 plus y1, so y0, that's that vertical height, plus y1, that's that vertical height, divided by 2, which is what the formula says, multiplied by h, and that's the distance between them, that's the area of the first strip. Now I do the same thing for all the other strips, and what I do then is I take out a common factor, which is h over 2, then add together what's left, and then I'm going to simplify it. Now if you look at these, the first ordinate and the last ordinate is only used once. The middle ordinates are used twice. So you have the first ordinate and the last ordinate plus 2 times the sum of the middle ordinates. And the formula that you see in the formula book is going to be quite complicated, but the way I like to remember it is this. The area equals h over 2, so that's the height or the distance between each of those ordinates divided by 2, multiplied by the sum of the ends, so that's what I've got over here, plus 2 times the sum of the middles, okay, and that's what I've got over here. And I'll explain in a bit more detail what that means once we get onto an example. The other thing we need to be aware of is whether we're overestimating or underestimating the area. If you look at the graph on the left, the orange line is the curve, and the area underneath it is going to be underestimated by using these trapeziums. These little bits I've shaded in red are the bits which haven't been included in this area. Okay, so on the left here you'd get an underestimate, whereas on the right you get an overestimate because the trapeziums go over the curve. Okay, so these bits these bits which are shaded in red are the extra bits which would be included in the area of these which you don't actually want. Okay, so in this case you'd get an overestimate, and in this case you'd get an underestimate. So if you have a graph, you'll often be asked whether the approximation that you're getting is an overestimate or an underestimate, and just think about whether the trapeziums you draw will go over the curve or whether they'll fall short of the curve. So on to our first example. It says use the trapezium rule with 4 strips to find an approximation for the following integral, and that's e to the half x. And then what we're going to do is, by considering the actual answer, we're going to calculate the percentage error in the approximation. Now one mistake that people make when they're using the trapezium rule is they actually try and integrate the function. Remember, the whole point of the trapezium rule is to get you an approximation for that integral. So what you do instead is this. Make yourself a table, so you've got your values of x, and because the integral is between 1 and 5, and you've got 4 strips, that means x will equal 1, 2, 3, 4, 5. Okay, remember that's going to give us 4 strips, so if I just draw those here, you got 1, 2, 3, 4, 5. Okay, so 1, 2, 3, 4 strips. So these are our ordinates, these are our x values, and what I do then is work out the corresponding y value. So e to the half x, so e to the half in this case, and e to the 1 over here. This will be e to the 3 over 2, e to the 2, and e to the 5 over 2. Remember, it's e to the half x. And then what I do is I put in my weightings. And what I mean by that is this. It says you do the sum of the ends plus 2 times the sum of the middles. So what I do is I multiply the ends by 1, okay, which means you don't really need to do anything to it, and then multiply the middle ones by 2. So this is still going to be e to the power of half. This will be 2e. This will be 2e to the power 3 over 2, 2e squared, and e to the power 5 over 2. Now, if I add all these up, what I'll end up with is this bit in the brackets, okay? And all I need to do then is multiply by h over 2. So that's the distance between each of these ordinates divided by 2, which in our case is a half. So what I can do is enter all these into the calculator, and I'm not going to do any kind of rounding or anything like that because I want to keep everything as accurately as possible. Some people tend to write out the decimals and then add up the decimals, but that introduces error, and we try to limit the amount of error we introduce. So I'm just going to put this into the calculator, and what I end up with is 43.009, and it just carries on. And I leave the actual answer, well, this answer, on my calculator display. So what I need to do then is A equals h over 2 times by 43.009. Okay, and in our case, h is 1. That's the distance between the ordinates. The distance there is 1. Divided by 2 gives me a half. So it'll be half times by 43.009. And I end up with 21.505 to 3 decimal places. Now again, I'll store that answer in the memory just to keep everything as accurately as possible, but that's part A of the question done. Now for the second part, we need to calculate the actual value of the integral. So what we do is we integrate between 5 and 1, e to the power x over 2 dx, and that's quite straightforward. It's e to the power x over 2 divided by a half, which is the same as multiplying by 2, and my limits are 5 and 1. So that would equal 2 e to the power 5 over 2, take away 2 e to the power a half. And if I do that, I get 21.068. And again, I'm going to restore that answer in the memory, so I've got the actual answer in there. And what I do then is work out the percentage error. So to work out the percentage error, it's equal to the difference between the two numbers divided by the actual answer multiplied by 100. Okay, so that would be 21.505 take away 21.068 divided by 21.068 multiplied by 100, and I end up with 2.07% error. Now in this case, we can see from the actual answer that the original estimate was an overestimate. Okay, and if the question asks how can you improve your estimate, all you need to say then is you need to increase the number of strips, because if you increase the number of strips, the little trapeziums that you get will closely match the curve. It will match the curve a lot better than big strips will. So that's a standard answer to those kind of questions. So on to our second example. It says using 5 ordinates, find an approximation for the following integral, and it's the square root of 1 plus tan x between pi over 3 and 0. And just remember, make sure your calculator is in radians mode. Now I've got no idea what this graph looks like, but what I am going to do is draw myself my 5 ordinates. Okay, so 1, 2, 3, 4, 5. Okay, so it goes from 0 to pi over 3. So in the middle of that, you've got pi over 6, and then you've got pi over 12, and this will be pi over 4. And whilst I'm here, I might as well work out what h is. Okay, in this case, h will be pi over 12. So all I need to do now is set up my table. So I've got x, which is my ordinates. So 0, pi over 12, pi over 6, pi over 4, and pi over 3. And then the corresponding y values. So this will be the square root of 1 plus tan 0. And the others are going to be 1 plus tan pi over 12, 1 plus tan pi over 6, 1 plus tan pi over 4, and 1 plus tan pi over 3. And I'm going to put the weightings in with this now as well. Okay, so this is going to be y, but with the weightings. Okay, so this is going to be 1. I'll just put the 1 there just so you can see, and these will be 2. And because these aren't going to be nice values, they're not going to be that straightforward to enter into the calculator. I'm not going to do all the decimals, but I'm sure you can enter all those into the calculator. And what you'd end up with is 10.24524, and it just carries on. Okay, so that's that bit then. So that's the bit inside the brackets that I've calculated. And all I need to do now is work out what the integral is, and that will be approximately. Now I need to do half of h, so pi over 12 divided by 2 would be pi over 24, multiplied by 10.24524, and what I end up with is 1.341 to 3 decimal places. Okay, so that's my approximate integral of this. So on to our final example. We're going to use the trapezium rule with 4 strips to find an approximate value for the following integral. And then what we're going to do is we're going to work out the actual value of the integral and see the percentage error. Now I've taken the time to start this off for you just so that we save a bit of time with the video. I've drawn my strips. Okay, so I've got 4 strips and these are my ordinates. Okay, and these give me h equals a half. Alright, these are my values of x, so these are my ordinates, and these are the corresponding substitutions for y. Now the first one, in this case, 0 times the square root of 2 take away 0 will be 0, so that one I can just put as equals 0. This one here will also equal 0 because 2 take away 2 is 0, and 2 times 0 is 0. Okay, and it's just these ones here that I need to worry about. And even this middle one is quite straightforward because what I end up with here is 1. Alright, so what I need to do is I need to do 2 times each of these. Okay, so rather than being 1, that's now going to be 2. And then whatever these are over here, when I add them together, I end up with 5.346, etc. Okay, and don't forget to store the actual answer in the calculator. So the answer, so the final answer, let's just say I for the integral, is approximately, remember it's h over 2, so half divided by 2, which is a quarter, multiplied by 5.346, which gives me 1.337 to 3 decimal places. And again, store the actual answer on your calculator because that's going to help you with the next part. Now the actual integral is a little bit tricky and we're going to have to use a substitution to help us out here. So I'm going to say let m equal 2 take away x, which means dm by dx equals minus 1, which means dx is equal to minus dm. Now whilst I'm at it, I'm also going to rearrange to make x the subject, so x equals 2 take away m. And what I'm going to do is I'm going to plug all this into my integral. So my integral is going to become, I'm not going to worry about the limits just yet, x is going to be 2 take away m, and then I've got the square root of 2 minus x, which would be the square root of m, and I'm going to write that as m to the power of half, and dx becomes minus dm, so that'll be minus dm, but I'll just put the minus that side of the integral, which is fine. Okay, so that's my integral, and I'm just going to expand these brackets here, so I'll get 2m to the power of half, take away m to the power 3 over 2 dm, and now I can go ahead and integrate that. So I'll get minus, I'll get 2m to the power 3 over 2 over 3 over 2, take away m to the power 5 over 2 over 5 over 2. Okay, and like I said, I'm not worrying about the limits just yet. Now this here becomes minus 4m to the power 3 over 2 over 3 take away 2m to the power 5 over 2 over 5. Okay, and now what I'm going to do is I'm going to work out my limits. Remember, my original limits were in terms of x, but these limits are going to have to be in terms of m. Now if m is equal to 2 take away x, 2 take away 2 becomes 0, so the upper limit is 0, and the lower limit, 2 take away 0, is 2. So these are the numbers I'm going to plug in, and in that order. Now if I put in the 0, I'm just going to get 0 because 0 to the power anything will just be 0. So it'll be 0 take away minus, so it ends up being a plus, and now I'm going to put the 2 in. So it'll be 4 over 3 multiplied by, now 2 to the power of 3 is 8, that'll be the square root of 8, which is 2 root 2, take away 2/5. Now 2 to the power of 5 is 32, the square root of 32 is 4 root 2, and all of that gives me 8 root 2 over 3, take away 8 root 2 over 5, which is 16/15 root 2. So that's the actual value of the integral. So now I can go ahead and work out the percentage error. So the percentage error equals the difference. Now I don't know which of these is bigger. I don't know if this is bigger than this or the other way around. So it's the absolute value, or you can actually say the modulus of 16/15 root 2 take away 1.337 divided by the actual value, which is 16/15 root 2 multiplied by 100. And if you plug that into your calculator, you'll get 11.401%. Okay, and that's to 3 decimal places. Now, as you can see, that's quite a significant difference. Okay, we're quite a long way off. So if the question did ask, how can you improve your answer, you'd say by using smaller strips. Okay, and that is always going to be the answer to that question. And that's the trapezium rule done. One of the main obstacles you're going to face is being able to use your calculator efficiently and having good calculator skills, because that's where things can be problematic. But other than that, I've shown you the method for using it. I hope that's helped you to understand the trapezium rule. So thank you for listening, and thank you for watching, and hopefully I'll see you again next time. Goodbye for now.